Hey everyone, this is Chicken Math 3.14, and what we're doing today is we're going to do the 1.7 rational functions in behavior.
Okay, guys, so these are the learning objectives. We'll just be talking about horizontal asymptotes, how to find them, rational functions, slant asymptotes, and how to find end behavior.
All right, so first we're going to introduce the rational function, and it's basically the ratio of two polynomial functions. So f of x is a rational function, and you can see there's a polynomial over another polynomial. So that's what we mean when we say rational functions.
So what are asymptotes? So an asymptote we define as a line that a curve of a graph gets infinitely closer to as you go along the curve. So it'd be like if we were walking along a path and at the very beginning we took really, really long strides, but as we kept walking across the path, our steps got smaller and smaller towards the end. So the function to the left, we see this graph here, it has two asymptotes. So we have a vertical and a horizontal. And we can see this with the graphs that we have here. So we can see the red line vertically, it gets closer and closer to the green. And also just the same thing horizontally. We can see that in two places on the left and right hand side and on the top and bottom.
Okay, so we'll be talking about asymptotes and rational functions. So here we're given the function g of x, and when n, which is the degree in the numerator, is equal to d, which is the degree in the denominator, that means there is a horizontal asymptote at the leading coefficient of the numerator divided by the leading coefficient of the denominator, which in this case is just a divided by b. If the degree in the denominator is greater than the degree in the numerator, so d is greater than n, that means there is a horizontal asymptote when y is equal to 0. And when the degree in the numerator is greater than the degree in the denominator, that means there isn't a horizontal asymptote. But we could have a slant asymptote if the degree in the numerator is 1 greater than the degree in the denominator. And we'll talk more about slant asymptotes in the next few slides if you're confused.
Okay, so we talked about what a horizontal asymptote was, but now we're going to look at an example. So a horizontal asymptote occurs when the degree of the numerator is equal to the degree of the denominator. And if they're equal, then we can divide a by b to get the horizontal asymptote, where a and b are the coefficients of the highest degree in the numerator and denominator. So if we look at this example of g of x, we notice that the highest degrees are x to the fifth. So we can take the coefficients in front of each of those. We have 4 and we have 3, and we can divide those, and that gives us our horizontal asymptote of y equals 4 over 3. Okay, so this is an example of g of x, which we just looked at. So we can see y equals 4 over 3 here, and we can see on both sides that the graph gets closer and closer to this line. So that is our horizontal asymptote, y equals 4 over 3. And what we did is we just took the leading coefficients because the degrees are equal, divided them, and we can see a visual here.
So now we're going to be doing some practice with identifying the horizontal asymptote of rational functions. We're going to look at g of x. So the main thing is to look at these degrees of the numerator and the denominator, and that's going to be telling us information on the horizontal asymptotes. So the highest value in which x is raised to. So if you look at the numerator, x to the 72nd, that's the highest value where x is raised to in the numerator. And then the denominator, it would be 91. So our degrees that we're looking at is 72 and 91. Now, 91 is greater than 72, which tells us that the denominator's degree is greater than the numerator's degree. So our horizontal asymptote will be at y equals 0. So curves on this g of x function will be approaching the line y equals 0. All right, next we're going to be looking at p of x. So our degree in the numerator is going to be 3, and our degree in the denominator is also going to be 3. So since our degrees are equal in the numerator and the denominator, we're going to be looking at the ratio of our leading coefficients. So we have 960, and then we have 100. Those are our leading coefficients. So 960 divided by 100, you're going to get 9.6. So that tells us that our horizontal asymptote for p of x will be at y equals 9.6. All right. And then lastly, s of x, our degree in the numerator, well, it's going to be 5. and our degree in the denominator is going to be 2. So since the degree in the numerator is greater than the degree in the denominator, so 5 is greater than 2, we're not actually going to be having a horizontal asymptote.
All right, guys, for our second example, we will be trying to find which equation best represents this graph. So you can pause real quick if you want to do it. So the answer is B, and I'll go through each of the answer choices explaining why it is or isn't that answer choice. So for A, since the degree of the denominator is greater than the degree of the numerator, the asymptote would be at y equals 0, the horizontal asymptote. For B, since the degree in the numerator is equal to the degree in the denominator, we can divide 9 by 3, and that gives us 3. And if we look at the graph, we can see that the lines are both approaching y equals 3. And for C, since the degree in the denominator is greater than the degree in the numerator, the horizontal asymptote would once again be at 0. And D, the degree in the numerator is greater than the degree in the denominator, so there isn't any horizontal asymptote.
Slant asymptotes. If the degree in the numerator is greater than the degree in the denominator by 1 in any function, long divide the polynomials to find the point slope form. This is the equation of the slant asymptote. So for example, we have here g of x is equal to x cubed plus 4x plus 5 divided by x squared plus 2x minus 1. We can see that the numerator has a degree of 3 and the denominator has a degree of 2. And since 3 is 1 greater than 2, we know that we can find a slant asymptote by long dividing. And so we can see that the quotient from dividing the numerator by the denominator is x minus 2. And we ignore the remainder for finding the slant asymptote. We can see here the work that I did for this problem, dividing the numerator by the denominator, and we can see that we actually get a remainder of 9x plus 7. So we ignore this remainder and we only keep this quotient. Remember to long divide your polynomials if you ever find them in a fraction where the numerator has a degree 1 higher than the denominator.
All right, so we're going to do an example where we're going to be looking at the slant asymptote of a rational function. So determine the slant asymptote present in the graph of m of x. So we're right here, we're given m of x, which is a rational function, and we know that we're going to have a slant asymptote because if we look at the degrees, 2 in the numerator is our degree. Our degree in the denominator is 1. The degree in the numerator is greater than the degree in the denominator by 1. So we know that we're going to have to divide these two polynomials to be getting our slant asymptote. So here's what we get when we divide 3x squared plus x minus 2 by 2x plus 6. It's just long dividing polynomials, which you should know how to do. So, and of course, we ignore the remainder and we just look at quotient that we get. And that would be our slant asymptote.
So now we're going back to the end behavior of rational functions. So here we see our function f of x, and in this function, when n and d are equal, the degrees of the denominator and the numerator are equal, a over b is actually where the left and right ends go. And we can call this c. So the coefficients of the numerator over the denominator, where this equals c, this is what the function heads towards. This is the horizontal asymptote. Now, for the degree, when the degree in the denominator is greater than the degree in the numerator, when n is less than d, this means that their left and right ends go towards 0. So this should make sense because if the denominator's degree is greater than the degree of the numerator, it sort of overtakes that, and everything just heads towards 0 no matter what direction it goes. Whether to the left or the right, it always goes towards 0.
Okay, so now we'll be talking about end behavior of rational functions when the degree in the numerator is greater than the degree in the denominator. So when this happens, the end behavior is the same as the end behavior of the equation you get when you divide the two polynomials. So if we divide the two polynomials and we get negative 2x to the third plus 3x minus 1, then the end behavior of the function will be the same as the end behavior of negative 2x to the third plus 3x minus 1. So in this case, as the input values decrease without bound, f of x will increase without bound. And as the input values increase without bound, f of x will decrease without bound. So when the degree is in the numerator is 1 greater than the degree in the denominator, we know that this would be a slant asymptote. So the end behavior of the function would be the same as the end behavior of the slant asymptote. So if the slant asymptote is y equals 2x plus 4, then the end behavior of the function will be as the input values decrease without bound, the output values will decrease without bound. And as the input values increase without bound, the output values will also increase without bound.
All right, so now we're going to be looking at an example where we're going to be finding the end behaviors of a rational function. So right here we have h of x, and we want to be looking at the degrees. So the degree in the numerator is 4, and the degree in the denominator is 2. So since the degree in the numerator is greater than the degree in the denominator, we're not actually going to be having a horizontal or slant asymptote, but we can still find the end behavior by long dividing our numerator and our denominator. So right here, you can see how we long divided. And your quotient that you get is negative 1/2 x squared minus 1/2 x minus 1/2. So we're going to be looking at the end behavior of this equation. So if it was y equals whatever this is. So again, just to refresh, to find end behavior of a polynomial function, we're going to be looking at the degree and then the leading coefficient. So we can see here that if we looked at this as a polynomial function, we have an even degree and a negative leading coefficient. So even degree tells us that our left and right hand end behaviors are going to be the same. And our negative leading coefficient tells us that our outputs are going to be decreasing without bound. So to write that limit statement out, you're going to say as x decreases without bound, so this is our left-hand side, we're going to be going towards negative infinity. Our output values are decreasing. And then on our right-hand side, we're also decreasing since we have that even degree that tells us it's the same on both sides. So just by looking at our quotient, we can determine the end behaviors of h of x, so this actual rational function, based on the end behaviors of our quotient.
All right, guys, so we're on to the fourth example, end behavior of rational functions. So here we're given s of x, and we are told to identify a horizontal or slant asymptote and find the end behavior. You guys can pause and do it real quick. So since the degree in the denominator is greater than the degree in the numerator, we know that there's a horizontal asymptote at 0. So as the input values decrease without bounds, s of x approaches 0, and as the input values increase without bound, s of x also approaches 0.
All right, so now we're going to go to our fifth example of end behavior of rational functions. So if you want to take a second and pause the video and do it yourself. Okay, so we see g of x, and we see that it has 24x cubed on the top and negative 6x cubed on the bottom. So we can recognize that the degree of the top and the bottom are the same. So because they're the same, we can just divide the coefficients of the top and bottom. So we see 24 on the top, 6 on the bottom. It's important that it's negative. So we do 24 divided by negative 6, which is negative 4. So when we go to the left, to the negative side, it goes to negative 4. When we go to the right, it also goes to negative 4. So our horizontal asymptote is that y equals negative 4.
All right, so here is kind of an AP style question that we're going to practice because you're going to have to get used to the formats and the way things are worded for the AP exam. We're given the rational function r of x, 2x squared minus 13x plus 30 over x minus 3. So which of the following statements is correct? So we have A, B, C, D. So it looks like we're going to be seeing if it has a horizontal or slant asymptote, and then we're going to find out the equation of whichever asymptote it is. So we want to look at our degrees. So our degree in the numerator is 2, and our degree in the denominator is 1. So since our degree in the numerator is greater than the degree in the denominator by 1, because it's 2 and 1, we know that we're going to be having a slant asymptote. So we know that A is out. Now remember, to find the slant asymptote of a function, we're going to be long dividing the numerator by the denominator. All right, so we're going to be long dividing this polynomial at the top by this polynomial at the bottom. So when you long divide, you're going to be getting 2x minus 7. Of course, you don't use the remainder. So we're going to look at for our options, and we can see that D says the graph R has a slant asymptote at y equals 2x minus 7. So D is going to be our answer.
That's all for 1.7 rational functions and in behavior.
Hey, and make sure to subscribe for more chicken math content in the future.
Bye, guys.
Bye.
Bye.